One of the conclusions of the theory of relativity is that there is no absolute motion in our physical reality. Every object that moves in relation to some other object, used as a reference. If you move relative to a building, the building moves relative to you. If I were in a vacuum, I wouldn't have references to whether I was still or moving. How to explain this paradox? The Earth is located 150 million kilometers from the Sun, on average. If there were no absolute motion between them, the Earth and Sun would not change their physical positions in space, despite the relative motion between them. In that case, the universe should be static. Physics would have found a reasonable solution to the problem, and which tells us that the space that connects us with our star is now stretching, sometimes contracting, in an exclusive way. This interpretation is the same used by astronomers to explain how galaxies would be moving away from each other during expansion without abandoning their physical positions in space. In any case, if absolute motion did not occur in space, one might think that relative motion would be time-managed, as it is part of the space-time continuum. Not by chance, our dimension is called space-time. Thus, outside of time there would be no movement. There are places like that in space, where you can't measure time directly. This is the case of black holes, and the interior of the future-like cone of events. Newton's laws, in general, are applicable only within spacetime, since here, time appears to be a real and measurable entity. The time variable is present in the velocity and acceleration formulas, as well as in the forces. If the relative motion of galaxies was dependent on the behavior of space in relation to their masses, we could cite two possible hypotheses. 1. The masses of stars would directly bend the space around them, predisposing them to relative motion between them. This hypothesis is currently the most accepted. 2. Space would act directly on the masses, but the reverse would not be true. In this case, the relative motion between the stars would be dictated by the resulting variation in the density of the stellar masses. That is, the total mass of a star would not change significantly in a short period of time, but its volume and total brightness would. If the volume of the star were to decrease, there would be a greater concentration of its mass, and it would tend to shine less, and to attract another star closer. If its volume increased, the tension between them would decrease, and they would move apart, glowing more intensely. It would be impossible to prove, in practice, both the first and the second hypothesis. Is that the measurement of the curvature of space is done indirectly. You assume space is curved because someone tells you that indirectly. That someone is light or cosmic radiation, as a whole, acting as if it were the messenger from space. Were it not for these two, we would not be able to know that stars actually exist. Who provided the information that space would be warped by solar mass during the 1919 eclipse was light from distant stars. This light was captured by cameras, which showed the position of the stars in the background, before and after the eclipse. Here, our problems begin. Could we blindly trust the space messenger? What would be the nature of your behavior? Is it true that light performs a simple harmonic movement, composed of two phases? Is it true that, in order to be registered by our measuring devices, this light must first be packaged or quantized? The questions outnumber the answers. If the Sun and Earth did not abandon their physical positions in space while moving relatively in time, the variation in the curvature of the space that shelters them would be decisive. either by direct influence of the masses or by the independent capacity of space to generate inertia. The curvature of space would be intricately related to time. A static space could not house time. Time would have to be part of another universe that was not stationary, set apart from the real. In this other temporal universe, relative movement would prevail. Physicists assume that light would propagate in two-dimensional space, in the form of circular waves. However, they could not move from the center if the one dimension of time was not added to them. They cite, as an example, the waves that would be formed when a stone was thrown on the surface of a lake. By adding time to the two-dimensional surface of space, we would obtain a three-dimensional and straight cone of light, allowing the waves to gradually move away from the source. This type of circular wave propagation does not allow predicting the dissociation between the energy levels of light, as would be the case with ultraviolet and infrared. In the case of a planet revolving around the Sun, the circular motion would describe a state of rest, with no movement towards or away from the star. This would also happen with electrons, as they rotate around the nucleus of the atom. The use of the Doppler effect would not make sense in this case, as light could not be polarized by adding the one dimension of time. The polarization would be expected when you took the time variable from the cone of light and flattened the cone over the original two dimensions of space. Doppler would depend on this polarization of light, even if it remained a trend that would have been suspended to infinity. The suspension of the redshift to infinity, motivated by the contraction of time, would be, in this case, the confirmation that the universe would tend to become flat at the subatomic level, even if this condition could never be reached. It's just that we need the curvature of space to be conserved, and the flattening tendency to remain suspended to infinity, so as not to hurt the uncertainty principle. Why is it said that this would happen at the microscopic level, and not the astronomical scale? Because, when you flatten the future light cone, by stretching space, you would contract time to subliminal levels, which would point to the apex of that future light cone. Making use of the Doppler effect is to ignore the curvature of space, and neglect the uncertainty of the position of light sources. The explanation, so far, shows why circular motion predominates in the night sky, with the stars moving, in blocks, from east to west. Starlight appears to be hiding some of the relative motion that the stars would assume in space. In the remote past of mankind, the observation of stellar movement created immense difficulties, leading us to believe that the Earth would occupy a privileged position at the center of the universe. Johannes Kepler managed to unmask the circular motion, placing the Sun at the center of its planetary system. If it were real, the circular motion would tell us that the Earth would always be moving at the same distance from the Sun. When we transfer the Earth's motion to our star, the latter seems to move across the sky with constant speed and acceleration. That is, the light tells us that the Sun would be shining exactly 150 million kilometers away. The 8-minute time that its light would need to reach Earth would also remain unchanged. However, according to Alberta Blair, at aphelion, which is the furthest point from the Sun, the Earth would move at 152 million kilometers away. At perihelion, our planet would approach 147 million kilometers. An insignificant difference, at plus or minus 2%. If the Sun retained the same mass and volume over time, as circular motion tells us, it would have to manage the orbits of all its planets, through a single curvature in space. The solar system would be plastered, in that case. We know, however, that it is a dynamic structure which changes from moment to moment. Furthermore, planets of peculiar physical characteristics have mass and density which differ from each other. By preserving its mass and volume, our star would always retain the same brightness, which would give it the behavior of an incandescent lamp. The farther a planet is from the Sun, the less light it should receive. These problems would be solved if we assumed that, even without direct recording, the Sun's mass could be assuming different densities and volumes over time. Thus, even if the star's mass did not change significantly, variations in its density could be related to different curvatures of the space around it at different moments in time. This would have direct reflections on the orbit of each of the planets, as they could be captured by the Sun in a particular way. That is, Earth and Jupiter would obey different curvatures of space at different moments in time. When NASA sends a probe to Jupiter, technicians are forced to correct its trajectory over time, adapting the probe to these transient variations in the curvature of space. Without that, the probe would not reach its destination. As there is no absolute movement in space, the planet to be reached would not move from its corner. Something similar happens with a cork floating in the sea when hit by a wave. It rocks up and down, but doesn't move from its seat. We must remember that, under these conditions, the motion of the planets would only be relative, as it would occur in time and not in space. Thus, time would forever be indexed to the continuous curvature of space. Without curvature, there is no time, and vice versa. This alternative interpretation does not have the official signature of science, so it should be viewed with reservations. Even so, the possibility that the veiled variation in the density of the masses manage the relative movement in space would be an interesting point to be considered. It seems evident that we depend on light to make almost all of our conclusions about the nature of the visible universe. Light does not lie, but, as we saw in the case of circular motion, it can induce interpretive errors that could be avoided. A paradigm shift would require a lot of boldness on the part of our scientists.